Okay, so chapter 12, Functors. We're going to finally delve into functors, a very powerful abstraction, pilfered from category theory in mathematics. We won't dive too much into category theory here. Concentrate on motivations for using this abstraction to help solve programming problems. Cool. Okay, laying some groundwork. When we define an algebraic data type, such as maybe, we have an idea of what the type represents. The capitalization so far has been a little strange. I don't know that all of these need to be capital. This one too, but whatever. We were talking about maybe being the type that holds a result. We've been talking about maybe being the type that holds the result a computation of a computation that can potentially fail. Okay, so typo, I think. Pretty sure. Let me write it down. The second. Result of a okay. But at this point, all we have is our intention. We haven't specified how it's to be used. Once we start adding type class instances, our intention becomes more explicit. So, okay, here's a type class instance for this thing. I think we do it like this. Okay, so let's fix this up a little bit. Okay, so we don't need this. The names are unnecessary now. And for this one, we need to say that A also has ORed, apparently. I think. And apparently we also need eq. Like this. Okay. Hey, Jebby, how's it going? You can give names to derivations. Yes, you can. Except that they're always named in this fashion. So it's always named type class and then type. So it's kind of like pointless. I don't know that this name is used for any reason. So like I don't think it's actually useful in practice. And they're like it's removed. Well, not removed. You can still write it, but it's like I think they're trying to deprecate it. Yeah, I'm not sure what the intention was, but you can remove this as of Purescript, whatever we're on. 11 something. What's the other one called? I think it's 14 or something like that. Okay, anyway. Every time we implement another type class instance, we are cementing the type's behaviors, choosing one possible behavior over all others. Doesn't mean we couldn't write code to sort maybe where just is sorted before nothing, despite the ORD derivation. The whole point of ORD is to dictate the behavior when comparing values of a type. Uh, okay. So you can usually have multiple instances, so attaching a name to them sounds kind of reasonable. World Center. Hey, how's it going, by the way? I feel like I haven't seen you in a little while. By Purescript by example, uh, type class instances are named to aid the readability of the generated JavaScript. Interesting. Um, so like we should be able to generate this pretty easily though, right? Like if we know the type class name, we know the type name, we could easily just generate that by concatenating their symbols. So I don't know. Maybe if we like actually gave them good names, it would be a different story. But I don't know what you would call this. Like I don't know what JavaScript gets generated, so I don't even know what I would name this. So I imagine it just creates functions like this, maybe in JavaScript land. Unsure. Anyway, okay. Um, this would be short-sighted and difficult to maintain. I work for small code bases, but it certainly doesn't scale or work well with multiple projects. Especially if compare maybe is different between projects. Um, Maybe I don't really understand this paragraph that well, but it seems like if you just shared this with a code base, it's no different than maintaining an ORD instance. Obviously not for maybe, but for your own types. So I don't know. Maybe I don't fully appreciate this paragraph, but that's okay. Okay, so here's mathematical equation. I feel like I haven't seen division written in this way in a really long time, which is funny to me. Um, we're going to write a function to divide where a division by 0 will result in nothing. Okay, sure. This looks reasonable to me. So we need to be able to say that the a's are equal. Otherwise, we can't compare y to something. We'll say it's a Euclidean ring so that we can get this 0. I believe we get 0, add 1, and multiply or something from a Euclidean ring. And then if it's equal to 0, we get nothing. Otherwise, we make the just and do the division. What happens if you just divide by 0? For something that's a Euclidean ring? Oh, interesting. I don't know that I like that idea, but okay. Maybe that's like part of the definition of a Euclidean ring that I don't know. Anyway, okay. So now let's compute our earlier formula. This one. Okay. Case divide. Yeah, so if we get nothing because we've given a 0, then we continue. Okay. We didn't explicitly specify that failure will stop all computation in its tracks. That was an implicit behavior based on the structure of the type. Nothing contains no values to continue with. All we can do is return nothing. This is not the case with either. Is this the British way to spell intention? What is one? Is that how you spell intention? And I'm really tired this morning. I guess that's why. Okay, that's what I thought. Also, it's different here again. What is our intention when we define this type? There could be two different possibilities. Either could be a choice, in other words, a logical or. Could also be a failure with reason, where left is the failure case and right is the success case, which is typically how I've seen either defined. With only this definition, though, we have no way to tell. Let's look at both intentions. First, failure with a reason by repurposing our maybe example. Okay, so instead of returning a maybe, we return either. We say left divided by 0 or right. Cool. And if we get a left, then we just continue with that left. Otherwise, we unwrap the initial result and rewrap it up after doing our computation. Cool. This intention is very closely aligned with maybes, hence the use of the same example. The major difference is that we explicitly short circuit left with either, whereas with maybe that choice is implicit due to the fact that nothing has no value. With the choice intention, we need to imagine a different use case. So we have convert. Sure. Here we have two valid values, and we can convert the left from an A to a B. So this is another typo, right? Here we have two valid values, and we can convert the left from an A to a C. Yeah, okay. Let me just quickly write that down. So we're on page 384. Third paragraph from bottom. Left from A to a C. Okay. Using G. Perfect. So that's right. We can operate on both sides since our intention here is to use either as a choice between two values of potentially different types. It could be better to capture the semantics of our intent by creating a different type that's isomorphic to either called choice. Yeah. Now our name better reflects the semantics of the type. Here's what our convert function would look like with our superiorly named type. Not sure it's strictly superior, but that's okay. I think that a lot of times when I've seen people do this as a choice, they just make it explicit. Like it's just a domain type that has like a more meaningful pick A or pick B name, and then it's a choice between those two things. That's obviously isomorphic to either, but like you know, it's a little more aptly named. I do like that, for example, in unison, it doesn't matter what you're using. You can just like rename anything that you want and you still maintain the behavior of the parent. So like you can just rename either to a different name and you still get all of the functions that are designed around either. So if you have something that's isomorphic to either, it's just either, and you can just use it, which is pretty cool. I should really check out Unison again because I think somebody wrote like an HTTP um, server for it or backend or something. So you could probably it's probably pretty usable. I'm gonna have to write some stuff, but I have too many projects. I can't go do that. Anyway, semantics. When we create a new type, we intend it to be used in a very specific way. This is the semantics of the type, and we have a few ways of defining those semantics: name, implicit, behaviors, and explicit. Okay, I don't want to read this section. Contexts. Value that gets wrapped up in a maybe is a very different situation than that same value wrapped in an either. We refer to this difference as a context. Okay, let's keep going. Those are just like very, I don't know, okay definitions of those things. We talked about how values are grouped by type and how types are grouped by kinds. For example, maybe's kind signature is typed type. Maybe takes a type and returns a type, unlike int, whose kind is type. Int is just a type, and either takes two types. Okay, if you like, you can get the kinds in the Purescript REPL. So what do I need? Huh? Oh, I wasn't expecting that, but it's fine. Like it's not Haskell, so sometimes sometimes you have that issue. Either kind, either. There you go. Type to type to type. Cool. Um, see, maybe an either look like functions, and we can conceptualize them as such. They are in fact type constructors, which is analogous to data constructors, which are also functions. Any type constructor that takes one or more parameters is a high kinded type. Int is not a higher kinded type because it takes no type parameters. We can draw analogies between value space and type space. It's a weird plot for table. I don't know. I think I would have done something different here. Notice the parallelism between value and type. Also, the parallelism between function and higher kind of type. Not sure how to use that terminology either, but okay. Functions with simple types. When we work with simple types, not higher kinded, we can write functions like this. Uh, cool. And then compose them. Neat. Composed. In mathematics, functions map from the domain to the codomain. The domain and codomain are sets whose elements are values. We say that a function maps elements in the domain to elements in the codomain, but in programming, our domain and codomain are types, and the elements are the inhabitants of those types. Okay. Here we show the composition of F, G, and H and their mappings from the set of type A to type B, and so forth. The inhabitants of type A are the elements of the type A set. And this image also holds true for repeated function application. Function composition, and application are the bread and butter of functional programming. To use atoms to make molecules. So, fun comparison for me. Notice how all our types are are simple types, like int, string, number. But what happens when we consider the case of failure? What if G could fail? Okay, it returns a higher kind of type. We can compose it with F without issue. And we can do function application with it too. But what happens when we want to compose or apply H? Where I find this like kind of confusing. Wouldn't we? Okay. Anyway, the problem is H takes. Oh, okay, so let me elaborate why I find this confusing. We've redefined G, so you're supposed to keep in context F, H, and then replace this G. I guess is the idea. Although I think we could have just like you could have just copied the set here. I think it would be a little easier for people maybe. Um, Problem is H takes a C, not a maybe C. We could rewrite H or make it a specialized version of H that takes a maybe, but that just opens up a can of worms. Our H function works with simple types, but not with higher counter types. Functors and monads solve these problems. We'll cover the solutions. These concepts are too often skimmed over in other texts and introduced far too early. We've taken hundreds of pages to get here. I don't know. I don't think like I'm not sure that it's necessarily a problem to talk about functors and monads early, right? Like I just think that you need to set people's expectations early. Like if you're going to introduce functors and monads early, you need to say, you know, these just give you access to these functions with a particular shape, right? And that's it. It's you're just putting puzzle pieces together. And if you want to like have a deeper understanding of these things, like just start using them and you'll get um, the intuition for using them, I think. Yeah. Okay, so functors to the rescue. We've introduced the notion of contexts earlier, and in our recent example, C is in the context of maybe. Um, our conundrum was how to apply H to the output of G. Let's write a function to help us apply H to a maybe. We'll start with the type signature. Apply H. C to D, maybe C. So we need to return a maybe D. Yeah, so now we're going to go through like some examples of why we can't do this. Cool. But we can do this, which makes sense. And then if we write our just case on the right side here, we would need to have just H of X. Cool. So now we can apply H after G after F. If we wanted G to also return a reason for the failure, now we have to write another function to apply H that works with either. Bell should be going off in your head at point. This is going to form. Am I? Do I physically shake when I do that with my legs in my camera? Yeah, I guess I do because, well, mostly because I'm literally moving. That's funny. Anyway, um, I was just noticing that I'm like uh bouncing my knees. All right. This is going to be a problem for all higher kinded types, and it is. We would like to solve this problem in a more general fashion, and as it turns out, category theory gives us just the right solution, the functor. Did the functor the functor and category theory must have come first, right? Like, was this called something else when people first did like higher kinded programming, or did this thing get called functor because it was used so often? I don't know a lot about category theory, so I feel like the math would have come first, right? And then the connection was made to computer science. Oh yeah, yeah. No, okay. So then it probably came first. Okay. We're probably gonna have to program with this. Here's the definition of a functor in Purescript. Okay, so we have our florals, we have our function a to b, we have our context as it's being called, and our value wrapped in said context will return a b in the context. Cool. When we used non-empty, it used f in its type signature. That's it for a functor. Okay. Anyway, and then we give an infix mapping for map. That's this symbol here. This symbol here is a little archaic for like newcomers, but this is used pretty much all over the place for to mean functor. And we're going to see more of these coming up, so just something to keep in mind. The map method allows us to apply the function a to b to the a within the context of f, and modify it without changing the context. This is an important point. When we examine the Functor Laws, we'll see why this is true. Yeah, pretty important. So, and the other thing is like when you use a functor, the shape of the context remains the same. Like if you have a list, for example, you're not going to be able to add elements to the list or remove elements from the list with a functor. You can only map over each of them. So the shape of the list is maintained when you use the functor instance. What do you mean? How is that not true? So if you have a set and you map, oh, I see. If you map like a const function onto a set, that's an interesting point. Okay, you win. You win this time, Yappy. Fair enough. So, let me provide context or more context, I guess. If you have with a list, that's true, but with a set, if you map every function or every element to another element, let's say one, then you'll end up with a set with only one element in it, the number one. So, you can't maintain the shape of a set if you map over it. Fair point. Is that still a valid? It must be a valid functor, I guess. Uh, okay, so here's our instance for the baby functor. Keep in mind this name is completely unnecessary if you don't want to add it. Does that look familiar? Map is a generalized solution for our specific one that we tried to solve with apply h. And then yeah, so now we can write f map g after f basically. Mm-hmm. So this dollar is replaced with the higher kinded version. Okay, two perspectives of map. Look carefully at the map type signature. We can interpret this function. Yeah, so this is another term you'll hear a lot. Is A and B is lifted into the context. Mm-hmm. There's another way to say it. I guess this would be the more category theoretic framing, right? I don't understand the first part of that, mostly because I don't understand homotopy theory. Uh, but for one category, okay, I'll have to trust you on that one. Okay. The power of abstractions. I don't really want to read this. Yeah, so uh yep, okay, so let's do apparently a little bit of category theory. Um I've bounced off of category theory about 4 times now. So maybe this will be interesting. I think we're on the fourth time. Although I do have this book here, which I have read a little bit of, the applied category theory book, but I'm just not I can't I can't stick to it. I just don't find it that interesting. I don't know if that's the right term, like, or the right way to say it. It just I would rather do like I'm a chemist by training, so it feels really impractical often. Okay. CT is an extremely abstract, and because of that abstraction, it can abstract over many areas of mathematics. The area we're concerned with is programming, and that's where we'll concentrate. Okay. I'm trying to like point out typos and stuff, so it's easy to fix. Hopefully. Um. Cool. Let's start with the definition. A category consists of a set of objects and a set of morphisms between those objects. Pretty simple definition, as one would expect with something so abstract. Now the devil is in the details. We get to pick what our objects and morphisms are, which depend on what we're trying to model. Since our interest is programming, we'll pick our objects as types and our morphisms as functions. This category is traditionally called Hask after Haskell. Maybe I'm confused. I thought I was under the impression that like Purescript would have its own category, and then it may or may not map directly to Hask. I don't recall this, so I'm just curious. I thought the Hask category was literally the category of Haskell programs, but maybe that's not exactly true. Anyway, and as always, there are laws. Each morphism F has a source object A and a target object B, and is written like some notation, and we say F is a morphism from A to B. Morphisms compose. There is an identity morphism for every object, and composition is associative if you can do this. Or, well, this whole thing. There it is. This is a lot to digest at once, but hopefully you can see a lot of similarities with what we've been doing in Purescript so far. Let's take all of this one step at a time, but with pictures. I like pictures. Here's the category C, the set of objects A, B, C, D, E. Okay, cool. They're just in there. In Purescript, A, B, etc. are types, and here is a morphism F from A to B. Okay. The morphism F morphs object A to object B. I feel like morphism morph. Oh. But since objects are types in Hask, when we write a function in Purescript, it morphs values of type A into values of type B. Mm-hmm. Yep, there's our identity function. Okay, here's function composition. Cool. Thanks to the definition of composition, but not all diagrams commute. We start at the upper left corner int with any value and go through identity horizontally. And then vertically through identity again, we end up in the lower corner with the same value. But if we start back at the upper left corner, what? I do not understand this picture with this at all. I'm not. I do like the typesetting in these pictures though, for what it's worth. I don't know what is being used here to do the pictures. Drawing non-commuting diagrams in category theory is a sin. I think I just don't like understand what they're trying to get at, because like these two arrows, I guess these are types. So like const 0 still gets you to the type int, but it's just like a confusing diagram or a weird diagram how to think about. But again, we're at like a higher level where like the actual numbers don't matter. Like 0 doesn't really matter. We're just talking about things that can go from int to int, and this just happens to be a morphism from int to int. And it has the same shape as the identity in this case, I suppose. Although I guess you would never write this because you would just write like int with an identity arrow, and then you would never write like this in an actual diagram, right? Okay. Yeah. Ugh. Okay. Well, let's look at some examples in Hask, starting with the show method. Um, we can pictorially represent this as this. What time is it, by the way? And for the int instance of show, we bring the JavaScript implementation. Okay. Yep. Okay, cool. Yep, cool. Okay, so far we've only looked at a single category and ways to morph objects in that category into other objects in the same category. This is what functions do. Excuse me. Um, okay, so functors that map back to the same category are known as endofunctors. So all functors in Purescript are really endofunctors, but everyone just says functors. There's another really important requirement of functors. Functors preserve categorical structure. In abstract algebra, functions that preserve the algebraic structure of, say, a group are called homomorphisms, I guess. Yeah. Here, functors are like homomorphisms since they too preserve the categorical structure. Okay. Um, if a object A has a morphism to object B, then a functor must preserve that same morphism between the objects when mapping them into the new category. Also, cannot drop any objects or morphisms when mapping, nor can it create any new objects or morphisms that weren't in the original category. Yeah. Yes. Are like. They are like homomorphisms. This is throwing me off the like part. So I don't think you can say functors are homomorphisms, but like same shape seems pretty reasonable. All right, so anyway, we can map our f. So this is the functor f between category C and category D, and through the functor you can write a morphism from A to FA, F to FF, B to FB. Okay, so homomorphisms are functors if you view the groups as categories with one object and the group elements as morphisms. Okay. Yeah, this stuff always is really hard for me to digest. It's just so many words. Um, yep. Okay, I said that. Cool. Okay, so there's a mapping A to FA and B to FB in Purescript. For that, we're going to have to wait for applicative functors. But here's a preview. Cool. Uh, okay, I think that's fine. Functor laws. There's no way to enforce the functor laws in Purescript. The burden is on the author of the type class to verify that their implementation abides by these laws. In short, these laws dictate that functors must preserve identity and composition. Uh, and these laws essentially just come from the category. Like if this wasn't true, then that picture above wouldn't be true. Yeah. So we did do this previously. There are tools for checking that composition works. I'm not gonna like read through this anymore. It's just okay. So verifying the functor laws for maybe. Um, So if we have identity and nothing, sure, cool. So what I want to say about this is just that there are tools to do this so that you don't necessarily have to do all of it yourself. And we did them, I think, in chapter 11. So let me just look. Uh, Maybe it was chapter 10. I don't remember where we did this, is the problem. But there's a package, Purescript. Quick check laws. It's called checkers in Haskell land, which is why I always have a hard time finding it for some reason. But you can use these quick check laws. So if we go look here and look for Functor, maybe Functor here, you can just like use this check Functor function, and it will check the identity and composition laws for some arbitrary instance, which is just like um, some generated instance of A in this case, or a functor F. Okay. I don't want to read through this. I've checked these laws like 100 times. All right, let's. Okay, so yeah, I think you're right, Teuton. Yeah. Okay, so bifunctor. We've seen that functor can only map one of the type parameters. To map two type parameters, we need to use something called a bifunctor. Here's the bifunctor in Purescript. So this looks very similar to that choice thing that we looked at before, where you have like an A to C function, a B to D function, and then an F of AB, and then an F of CD. And you can just like use this very similar to functor, except obviously you're mapping two things, and you require a higher kinded F that takes two type parameters. Okay, we no longer have to use choice A like we did with functor. That's because bifunctors F takes two parameters and so does choice. In other words, their kinds match. Choice is type to type, matches F type to type. Now we map both cases of choice since we have a tailor-made function for each. Choice is a sum type. But what about a product type? Can you think of a product type we can make a bifunctor? What about this one? Okay. Yep, there you go. Tuple, cool. Here we map both sides of the tuple every time. But what if we only wanted to map the left side of the tuple? We could write the following function. Lmap. Turns out that this function and our map are in the Purescript bifunctor library, bifunctors, and the module data bifunctor. Cool. Bifunctors in category theory. I think it's just let's return to the Hask category where objects are types and morphisms are. Let's look at a few things before we cross that bridge. First, let's refresh our memories regarding Cartesian products. Here's an example. Cool. Yep. Yep. We've talked about this multiple times. Uh, okay. Okay. So now we're talking about a new f that happens to be a bifunctor. Sorry, I'm becoming uninterested in category theory again. There's just a lot of text here to explain functor, which in my opinion is like really simple, and we shouldn't make it this complex. Like I just don't feel like you need to understand this to understand functor or bifunctor. Like they're just functions with shapes, and they obey some rules. It's not very complicated. I don't know. Maybe people don't like that I say stuff like that. Especially as a theorist, I suppose. I should be more uh I should be more theory driven. I'm just not anymore. It's like obey the rules, write the thing. Do people call these threeples? I always called them triples. Anyway, I'd be more surprised when something doesn't have a bifunctor instance that looks like one. Probably true. Okay, so anyway, you can use that same library to check bifunctor laws as well. Okay, so functors in perspective. Yep. Yep. Yep, that won't work. Cool. So we just fmap the thing. Cool. And that's that. Nice. Like, it's not that complicated. Look at the shape. Do the shapes match? Yes or no? The answer is no. And try something else. Okay, so I think I'm done for the day. Just yeah,